Thank you, Laura. Everyone, my name is Anand, and this is joint work with my fantastic collaborators, Yonatan and Aleksandrs. Okay, so this work is basically set in the setting of recommendation systems. So recommendation systems, as we all know, these are basically massive platforms which aggregate information from users. This could be information such as the reviews you left on a product, ratings of a movie, purchase decisions on Amazon, eBay, your engagement history on your favorite social media platform like Twitter or what have you. The platform then basically curates this information, presents it to subsequent users of the platform in order to optimize cumulative user engagement on a long run. So that's basically the goal of the platform in such settings. Now, a key challenge, as many of you might already know here, is that there could be a serious misalignment of incentives between the platform that basically wants to optimize some long-run metric, cumulative engagement, so to speak, versus users who are essentially myopic. They interact with the platform only for a subset of rounds, and they basically want to maximize their payoff over their duration of interaction with the platform. So there is this natural tension between cumulative payoff maximization, which the platform wants to do, and users being strategic. Okay, now one standard way in theory for the platform to mitigate this problem, which does not involve monetarily compensating users, is by exploiting what is known as information asymmetry. Now, information asymmetry essentially refers to the fact that the platform controls the flow of information to the users, which in a nutshell is sort of boils down to the fact that it knows much more than the user, so it can strategically reveal subset of information to the user so as to make sure their actions are what the platform would want them to basically be. So what is incentivized exploration? Incentivized exploration is now a very well-studied paradigm in econ CS literature, whereby the platform or the principle essentially leverages information asymmetry. It controls the flow of information to the users by selectively revealing information to the users. And it does so by basically providing signals to the users in order to influence their behavior and their eventual action on the platform. Now, to make this more concrete, I will give you a quick recap of what the classic paradigm is all about. So incentivized exploration essentially involves sequential T-round interaction between a social welfare maximizing principle and T myopic agents. There's been a lot of work on incentivized exploration now, and I'm basically just showing you a sampler here at the bottom of the slide. Each agent, basically, in the classic model, interacts with the platform or the principal only for one round. These agents, they are endowed with prior beliefs about the goodness of actions. More specifically, they have prior beliefs about the possible rewards that they could get by following any of the possible actions that they have access to on the platform. Now, as the game progresses, as this T-round interaction progresses, the principal accrues more and more information, and then it basically filters this information to nudge subsequent agents into taking desirable actions. Right? And this nudging basically happens by way of signaling. Now, as you can already guess, a desirable outcome in such a setting would be, well, you basically want you want users to comply with your recommendations, right? So that would basically mean that it should be rational for agents, essentially users of the system, to follow the principal's recommendation. Now, this recommendation could be implicit or explicit. I'll elaborate upon that in a couple of slides. And secondly, you want a mechanism to basically generate good social welfare, right? Because that was your first objective to begin with. Okay, so I'll give you a quick summary of what we are able to achieve in this work. So our work contributes to the extent IE literature by expanding upon the current state of the art along three practically relevant dimensions. First and foremost being private agent types. Now, previous work predominantly focuses on agent types being public, essentially meaning the fact that once the user comes to the platform, all of their covariates are observable to the platform. Our results actually extend to the setting of private agent types, where the platform may not be able to observe some of your covariates. Informative recommendations. By that, what I mean is the signal that the platform supplies to the agents in each round could actually be fairly complicated in the sense that it could be a direct action recommendation coupled with some supporting information. The most natural example of such an information structure would be ranking of actions, as opposed to just the top rank recommendation. Right? We're also able to handle correlated Bayesian priors with our work. Now, why are correlated Bayesian priors important? Well, because they actually encode detailed worldview of the agents. In reality, correlations have a natural way of modeling known problem structure, which basically this could greatly reduce the problem complexity and help make it tractable. So correlations are a natural property that one should be able to study. Prior work, by and large, was limited to basically independence assumptions across primitives of the problem. We're able to mitigate. Our workhorse here is a version of posterior sampling, which is a celebrated multi-unbanded algorithm. We pitched this as a general purpose solution for incentivized expiration. We provide theoretical guarantees for it, which, among other things, recovers the three objectives are highlighted above as corollaries, as well as all prior work on incentivized expiration via posterior sampling. We're also able to identify a key notion of data complexity, which sort of, in a way, also encapsulates the hardness of the incentivized expiration problem. And I'll talk more about it towards the end of the presentation. Okay, great. So that said, let me quickly introduce the classical model of incentivized expiration. So here, at the beginning, nature draws an unknown model U star from a known prior distribution P naught. The principle announces its signaling mechanism, which is essentially a protocol for how it is going to generate these signals based on whatever private information it has. Right? Now, the interaction protocol is as follows. In each round T, a new agent with type XT arrives. Now, these types are not adversarial. They're essentially fixed ex ante, but only revealed sequentially. So, I mean, in principle, our model can handle oblivious adversaries. The principle observes the public type of the agent arriving in type T, in round T, and based on that, it generates a signal MT using the policy pi. The agent observes the signal and pulls an action, which is basically from the index set 1 to k, collects a stochastic reward, collects a real valued stochastic reward yt, which is then observed by the principal. So at the end of the one round interaction, the principal observes the action that was taken and the corresponding stochastic reward. Now, the underlying economic assumptions here are quite standard. Payoffs are stochastic. So there's a fixed, publicly known mapping from models, types, and actions to the stochastic payoff, which is denoted by F. You could think of it as being the standard linear model. The rewards are actually corrupted by mean zero noise, which is again standard. And agents are Bayes rational in the sense that they are going to best respond to the signal that they received in round T, subject to their prior beliefs, which is P naught. That said, just to reiterate, the principal objective here is to maximize cumulative expected payoffs over T rounds of interaction. Great. So let me sort of quickly dive into what prior work essentially sort of does along these three major problem dimensions. So for private agent types, there has been some sort of like work which essentially dealt with a version of this model in a way where they essentially consider deterministic rewards. And the focus was somewhat different from what we're actually trying to do in this work. So Emolik et al. 2019, they focus on the problem of explorability of all type action pairs, which is a different objective from what we have in our work. And they actually propose a custom designed algorithm which turns out to be inefficient because it does not handle the explore-exploit trade-offs which are at the heart of our problem. Similarly, for informative recommendations, there's also some prior work which deals with some specific signal shapes, in this case being sub-history of previous interactions. And again, this paper basically provided some custom designed algorithm, but unfortunately its regret turns out to scale suboptimally compared to posterior sampling, which is what we're using. Lastly, there's also been some work involving correlated Bayesian priors, but unfortunately, they do have to relax on some other assumptions involving other primitives of the problem. What we have is this extension of posterior sampling, which basically does away with all of these restrictive assumptions and basically provides a comprehensive theory which unifies prior work and also spits out some new interesting results from these functions. So that's it. I'll dive right into what our proposed algorithm does. So we're calling it filtered posterior sampling, which will be clear for, as to why we're using filtered will be clear in a couple of seconds. So posterior sampling, by definition, guesses the model U at each time from a posterior distribution PT. So this is the posterior distribution of models given the history. This is the private information that the principal has. Now, based on this posterior distribution, the principal sends a signal MT to the agent, which implies a recommendation AT. AT is so correct. As to how that exactly happens is this. So the guessed model is basically passed through a filter. This filter is what we refer to as the semantic map. It transforms the principal's private information, which is the sampled posterior model UT, into a signal, into a meaningful signal, MT. This signal is further transformed into an implied recommendation by another mapping, which is called recommendation menu. This recommendation menu essentially takes the signal as well as the agent's true type as an input and spits out a recommended outcome. Now, we basically want this composite mapping to have some sort of a consistency with posterior sampling. Why? Because posterior sampling is what we actually want to implement because of its nice regret minimization properties. So the consistency would basically mean that the implied recommendation is actually the same as the best term recommended by posterior sampling for given the model UT and the agent type XT. So this is just to essentially ensure consistency of recommendations. Now, once this step is done, this basically illustrates how signals are generated given principal's private information. Once the agent sees the signal, they take an action AT, the principal thereafter observes the action AT and the reward YT that it generated and updates its posterior PT, right? So that's essentially the sort of like the protocol. Now, let me introduce this notion of incentive compatibility. So relevant to our setting, this is essentially called Bayesian incentive compatibility. Now, why do we need that? Well, we need that because we essentially want agents to comply with our recommendations. Now, what is the benefit of that? The benefit of that is, if they actually comply with our recommendations, we will end up implementing posterior sampling in some way, shape, or form. Why is that good? Well, that gives us optimal regret. So we need incentive compatibility, and the relevant notion here is BIC, which essentially means that the recommendation that the mechanism spits up, the implied recommendation, coincides with the agent's best response given the signal. Okay? All right, so let me sort of instantiate some canonical examples of semantic maps and what kind of signals they correspond to. So the simplest example would be direct recommendation, which is the classical paradigm study in prior literature. So here there are no private types, which essentially implies that the mechanism that is being implemented is the vanilla version of Thompson sampling. Here, the signal is basically just the best arm recommendation according to the observed type and the sampled posterior model. You could do something more complicated than that. Instead of giving just the top ranked action, you could give top K, or you could basically supply an entire ranking over actions, which essentially augments the information, the amount of information that the agent sees. And so that basically would be a relatively more informative signal. You could also go all the way to the other end by literally supplying this, the sampled posterior model as the signal itself. Now, this would basically work for private agent types under some assumptions, which I'm happy to discuss after. Okay, so essentially what we see here is that this semantic map transformation helps us modulate the amount of informativeness of signals. Okay, so before I state our main theoretical result, I think it's important for me to talk about, okay, what this is essentially based on. So we assume access to T0 rounds of what we call as warm-up data. Now this warm-up data is of the form, so these are essentially T0 tuples of the form type, action, and reward. So XT, AT, YT for some T0 number of rounds. And this is not subject to BIC constraint, which essentially means that you could collect this data either simply by paying agents and for T0 rounds, or you could, if you have access to data collected by some other algorithm, perhaps, even that would work, right? So we basically posit no condition, no constraint on how this data was actually generated or collected. Now, suppose we have that. Suppose we have access to T0 rounds of data. We're then able to guarantee that if the quality of this data is sufficiently high, which actually means that if the spectral diversity of this data is at least 1 over epsilon squared times log of some other parameter, then filtered posterior sampling is BIC. So it actually satisfies the incentive compatibility property that we're interested in. Now, what are these objects here? So first of all, the sufficiently small depends on the prior beliefs that the agents have and some aspects of the problem geometry. That's one. The spectral diversity, this is a non-traditional term which we are defining specifically for a problem, and we define it as the smallest eigenvalue of the empirical covariance matrix generated using the warm-up data. So this is a property of the warm-up data, right? So essentially, in simple terms, if the warm-up data is high quality, meaning it has, if all of its eigenvalues are sufficiently bounded away from zero, sufficient in this precise sense, then you're good to go. The min signal property is actually a design parameter. It's a property of the mechanism that you are designing. So it depends on the prior, the semantic map, and the geometry of the problem. Okay, now, when does this condition hold? Well, I quickly talked about it before. This condition can be ensured exogenously in the sense that you could either use prior work on incentivized exploration to make sure this condition holds for the warm-up data, or you could basically sort of do near uniform random sampling for T0 agents and basically compensating them appropriately monitored. So you could basically, you essentially need payments only for T0 rounds, and then you're good to go. Sure. All right. So key implication of this is that filtered posterior sampling actually inherits all the good properties of constant sampling, performance being the most important. And this then naturally implies sort of extensions along the 3 dimensions that I was talking about previously: private agent types, informative recommendations, correlated priors, as well as all previously known results for incentivized exploration and constant sampling. So I will conclude with this slide. There are ample of open questions in this area, most important one being lower bound, as to how much spectral diversity is actually necessary for incentivized exploration. What our work does is it provides a sufficient condition which actually matches state-of-the-art bounds from previous works, but still, as to what is the most relevant lower bound notion here is still remains an open problem. There are certain other aspects of the problem as well. For instance, what if the agents are actually long-lived, in the sense that they have repeated interactions with the platform? How would you modify appropriate problem notions here? And another angle which has sort of sparingly been looked at in previous literature is information leakage. What if you have, what if agents can actually see what previous agents did and so on? So I'll conclude with that and happy to take questions. Thank you.